Good afternoon and welcome to the quantum computing lecture. Last week, Professor Kuhnhardt taught his part in his introduction to the course, and I will continue with my part today. You will deal with Horst Kuhnhardt again in a couple of weeks. He will talk about computer architecture, but you'll see that in a couple of weeks since I'm running most of the course. In my last lecture, we started with systems, and concretely, we looked at deterministic systems, probabilistic systems, and quantum systems. What we worked with are, we represent our system as a graph, and we have a concrete state in that system, and we also established transitions between the individual positions. We started with deterministic systems, where we move a certain number of marbles around. We looked at how we can do this with matrices, and we established that mechanism. And then step by step, we evolved this and also started to use probabilistic systems in which we didn't move a certain number of marbles around anymore, but only one that is somewhere with a certain probability. And we also have transition probabilities in order to describe that. We did that, and concretely, we also used doubly stochastic matrices, and what we established was we have our matrix, and our state is represented as a column vector. We multiply it from the right in order to do one transition. However, if we can also multiply a row vector from the left in order to go back in time by one time click. And that's the mechanism we established. And then we continued with that and said we're not working with real probabilities between 0 and 1 anymore, but we're going to use complex probabilities. And the complex probabilities will allow us to describe a phenomenon called interference that we will deal with in this course. And we saw that a quantum state contains still probabilities, but this time it's complex probabilities. And the requirement is not that these probabilities add up to 1, but their modulus squared must add up to 1, or their absolute value squared must add up to 1. We saw one example state here. Remember, the states are always column vectors, but often in these slides, I use row vectors just that I can put it in one row, and then I put the transpose. So we are still dealing here with a column vector. And we also looked at an example system that we described and did some sample calculations and saw how we can transition from one state to another by always multiplying from the right to the matrix. And then we also saw what we finally need the adjoint operation for. That's something we had introduced in my first lecture. And we saw that if we use unitary matrices and we use U to do a transformation on V, and we multiply U dagger from the left, then U dagger times U is the identity matrix. So it eventually just undoes the operation. And that's also a property that will be key to quantum computing that we will see in the coming weeks when we dive deeper into quantum computing. We looked at a few examples like the quantum billiard game and the double slit experiment, and described some of these operations in terms of our matrices, and use state vectors that we transform into new states. That's what we did last week. And I also said or 2 weeks ago, and I said the superposition is key to quantum computing, so that we are in multiple positions or multiple states at the same time, so we can eventually get an enormous amount of parallel processing. I want to know from you if you're all okay with this so far. You probably had plenty of time for revision, and maybe just send me a green sticker if you're okay with what we did 2 weeks ago. If there are any questions, please send a red sticker, and I will wait for you. and you can go ahead with your questions. But with there being only green stickers, we can go ahead. Today, we will continue with systems. We will see how we can assemble multiple systems into a composite system. That's something that will be key to quantum computing as well, because so far we looked at systems, and in quantum computing, such a system would just represent one qubit, but we need many qubits for sophisticated operations. So we need to assemble qubits together into composite systems. And we will still today look at this more from a generic perspective. The qubits, they will probably come in as of next week or so. Today, we will finish how to assemble systems, and then we will dive a little bit deeper into quantum theory. And once that's done, we have all the tools ready in order to do quantum computing. So we will have two example systems now, and I think I will visualize them directly on the iPad because we need to look at them many times. So it's probably helpful if I copy them once. The screen share should be there in a moment. And so we will have two systems. I'll quickly introduce these two systems that we have. One is called GM, so system M, or it's called system M, and we plot the graph of M. We have a 0 position, a 1 position, and a 2 position. And there is a 1/3 probability to go from 0 to 1. So this is a third probability, and from 1 to 0 is a 1/6 probability. From 0 to 2, it's a 2/3 probability, and from 2 to 0, it's a 5/6 probability, and from 1 to 2, the probability is a third. And then what we have left is to go from 2 to 1. Here, the probability is 1/6, and there's a circle in position 1, which is a half. And we can also describe this as a matrix, which we will need later. So the matrix can be, as you know, just be derived from this graph, because the first row, so row 0, is all the incoming edges, and so there is no cycle in 0, but there is a probability to go from 1 to 0, which is 1/6, and from 2 to 0 is 5/6. Then the next row is 1/3, 1/2, and 1/6. For example, the 1/6 would be to go from 2 to 1, which is this one here. And the last row is 2/3, 1/3, and 0. And that's something we had practiced a lot 2 weeks ago. That's our first system. And we will now have a second system, and then we will assemble them, but I need to write them down and discuss them briefly with you so you actually see what will be going on. The next system doesn't have positions 0, 1, and 2, but one position is called an A, and the other one can be a B, so it can also be a character, and we'll use characters just that it's a little bit more understandable what we are doing. And we have these transitions, they are both 2/3, and then we have 1/3 probabilities just to stay. And as you know, we can convert this into a matrix. So we have the 1/3 in the diagonal, and the other two are 2/3. 1/3. And what I want to do now is I want to have a composite system. So I would assemble these two systems into a composite system. And since my first system has 3 possible positions and the second system has 2 possible positions, my composite system will actually have 6 positions. And I can now write down an example vector to describe just a sample state in this system. And what I'm doing here is I'm just using real numbers right now. So I'm working with just a probabilistic system, but all we're doing here can be totally applied to quantum systems as well. But just the introduction now to assemblies or to composite systems is just with real probabilities that it's easier to understand. Later today, we will be doing this many times with quantum systems. And now I would have 6 positions in my state vector because I have 6 possible states or 6 different positions I can be in. For example, what I also do is I usually add a comment on the left so I know what each row stands for. I could say, for example, the first row stands for 0A. So it's a 0 from the first system and an A from the second system. The next one could be a 0B, then a 1A, a 1B, a 2A, and 2B. So it's 6 possible positions I have. And these are just comments here on the left, just to highlight what each position here stands for. And I could say there's a 1 divided by 18 probability to be in 0A. Then 0B would be 0, 1A would be 2 divided by 18. The next one could be, say, 1/3, and 0.5. And all of this would just add up to 1, since we're dealing with regular probabilities. So this is what a state would look like. And often, if we work with these composite systems, we just add to the left of a vector or a matrix these comments, so that it's just obvious what each position here actually stands for. And now I want to build my composite system. And what I want, for example, is we'll start actually to visualize it and say there is, and it's just an excerpt of the composite system. So we are plotting now the graph of what this composite system would look like. For example, there is a 1A and a 1B. There's also a 0A and many more. And we can now try to calculate what these transition probabilities would be. So if I'm in 1A, where can I actually go? If I'm in 1, I could go to 2 and 0. So that would be in our original system. If I'm in a 1, I could go to 2 or 0. But now if I'm in 1A, we can check where I could actually be going. If I'm in 1A, I could be going to 1B because there's also an A and B in the second system. I could go to a 2A. I could be going to a 0B. There's also a 2B to which I could be going. And for example, 2A. So these are this is the graph now. I'm in 1A and there are 5 other positions I can go to. And now I need to wonder, what are these probabilities? How can I compute them in our composite system? And the rule is actually the following, and I'll write this here. If I'm, say, in IJ, so just generically now that I refers to the first system and J to the other system, and I want to go to I prime and J prime, I somehow need to calculate what that transition probability would be. And what I need to calculate here is, I say, well, if the first system is I would go into row I prime and a column I times, so this would give me a probability from my table or from my matrix M. And then I have the other matrix, which is N. And here I would look into row J prime, column J, because remember, the row is to which I'm going and the column is where I'm coming from. So I could calculate this, and we can check this now. Or maybe I'll let you think about it, maybe without looking into the slides. What I want to know from you is this probability here to go from 1A to 1B. If you have any guess what this could be, just by following these instructions, send it to the chat, please, without looking into the slides. And I'm curious to see what you think that probability could be to go from 1A to 1B. One student suggests 1/3. Well, let's take a look. We can look it up in the matrix, but we could also look at maybe more straightforward in the graph. So from 1A to 1B, that means we would stay in the 1. So this is 1/2. And we would go from A to B, and from A to B, it's 2/3. And let me just check the result. So that means it's 2/6, which means 1/3. So the student who suggested 1/3, this was correct. In fact, yeah, it's 2/6, so 1/3. And you can also look this up in the matrix or in the graph, but eventually you can fill in all these other ones if you want. It's a little bit tedious to do it, to calculate like this, the transition probabilities. And it turns out you can do this in a smarter way. If you remember, 2 weeks ago, or 2 weeks ago, I think, we introduced the tensor product. And the tensor product is M and the tensor product with N. And we looked at how that's defined. And eventually, this will give me a 6 times 6 matrix. And I have this matrix also in the slides, which I will show to you. And you can calculate the tensor product of M and N. And this will calculate you all the transition probabilities. And we can also see if I'm in 1A and I want to go to 1B, we said that's 1/3. So we want to go to 1B. So we have to look into this row. And we're coming from 1A. So that means 2/6, meaning 1/3. How to calculate the tensor product is something we discussed. So you've seen it before, and now you actually see what the tensor product is useful for. It's for calculating the transition probabilities in a composite system, which we'll be doing very often from now on in this course. So make sure you're familiar with composite systems and with the tensor product. All the slides in here is what I had just visualized for you on the whiteboard. These two composite systems, sample state, as well as how to calculate these transition probabilities by looking either in the matrix or the graph. But that's just tedious. So just use the tensor product and you have calculated this. And we said 1/3 or 2/6, and there are a few more probabilities in here that you can already find. And it would be your task maybe to complete this graph at home, to come up with the other probabilities, either manually or by taking a look here in what the tensor product returned, and you can try to complete this graph and compare it with your classmates. So there is another sort of scary or strange concept in quantum physics. It's entanglement. And it appears when you have two separate systems, and you can combine two separate systems with the tensor product. But then there can be states in this composite system which cannot be broken into these two separate systems anymore. And those so-called states are entangled states. And that's something we will also investigate in the next chapter when we look deeper into quantum theory, because entanglement is also a property that is relevant to quantum computing. Are there any questions from you so far about what we did now, building composite systems? If you're okay, again, maybe green reaction. If you're not okay, red sticker. All right, then we can go ahead. So today we'll be focusing on quantum theory, and once we are through that, we can finally focus on computations, but there are a few more quantum theoretical things we need to discuss. And once we have that, we can probably, as of next week, look into architecture and how to do quantum computing. You all had a chance so far to look at the course book of Janowski and Manucci. They, I think, wrote a terrific book, and I can highly recommend to you chapter 4.1, which makes a motivation why quantum mechanics is so important in our also daily life. This is not a physics course, so we're not discussing this in detail, but you're most welcome to read the book. Who of you has already had a look into the book in the last few weeks? Maybe just raise your hand or something here in Zoom if you have done that. I'm curious. You should definitely take the time to do further readings, because the course is difficult and you need to spend more time on further readings. Today, we will look in greater detail into quantum states. We've seen quantum states a little bit in the context of these systems that we have built now, but we'll formalize this and go deeper into quantum states. We will look more at superpositions. It's also a concept we only mentioned very briefly. We will look into it closer. We will briefly look at so-called observables, and then into how to measure a quantum system. We will look at dynamics, how a quantum system evolves, which is something we'll also need when we do quantum computing, because we do various computations in a certain sequence. And we will also see again how we can assemble quantum systems. We've now assembled simple systems, probabilistic systems. We will then assemble quantum systems, and then this effect called entanglement that I mentioned already will appear again, and we'll discuss it in greater detail and see how it's relevant to quantum computing. And then we have all the theory to get started with computing. We've mentioned in my last lecture 2 weeks ago the double slit experiment. And the double slit experiment is explained also in greater detail in the book. What appears in what we noticed, I'll probably just go back a few slides, when we looked at the double slit experiment, just trying to find it, just wait a second, which was this one here. And we discussed the double slit experiment and sort of noticed that, well, there are two ways to get from 0 to position 5, either through 1 or 2. But then we noticed when we squared this matrix, so we looked 2 time steps ahead, we saw there's actually no way to get to position 5, because these probabilities cancel each other out. We also formally showed that in my last lecture. And now when we look at quantum mechanics, this can be a little bit more generalized. Concretely, in the double slit experiment, what you would notice is you have a torch, and if you use the torch and you have these two holes here, or these two slits, you will have more light over here and less over there. But in the middle, there is no light. So if you put the torch here and it goes through, there's no light there. And that's caused by interference in the double slit experiment, because if you only have one slit, you close one, you actually have some light just behind here, as you can see there. But we have two holes or two slits, and then the photons cancel each other out. That's what the whole double slit experiment is about. If you have taken a physics course at university or advanced physics in high school, you may have learned about the double slit experiment. It's something that is super important to quantum physics, but in this course, we're interested in quantum computing, so we're not discussing physics experiment in great detail. If you're curious, there are a few more sentences on the double slit experiment in these slides, as well as in the book. As I mentioned, in the course book, there's one subchapter just focused on all of that. But now we want to describe quantum states, because that will be key also to quantum computing. And for this, I will probably show the essence again on the iPad. So it's not just looking at slides, but we actually develop a few examples interactively together. So before we also described quantum states, and now we'll define them more formally. And a quantum state is actually an n-dimensional, n-dimensional, and it's states. It's an n-dimensional column vector, and it's a column vector of complex probabilities. So C0, C1, and so forth, up to Cn-1. If you take a look into my slides, it's often row vectors, simply to save space, so I can put it all in one row. And that's why it's key to put the transpose in, because we always deal with column vectors. And now, if a point, or if our particle, our photon, for example, is at one point xi, so we have position x0, x1, and so forth, up to xn-1. At each position, we have this complex probability, a so-called complex amplitude, but we'll emphasize this term more closely today. We use now a new notation for this. And for example, I don't use just an X to describe the state, but I use a new physics notation, which I call, for example, psi ket. So psi is the Greek character, and this here is called ket, not like the animal, but K-E-T. That's how I pronounce it. So I say this is psi ket, for example. If I call it psi, as the Greek character says, and I put these signs to the left and right, then it's a so-called ket. That's the pra-ket notation that pra will discuss later today. And that's a physics notation that is quite handy. And actually, if we have this n-dimensional vector, it's actually composed of n basic states. And we have these basic states. For example, we have our x0 ket. And the x0 ket would look something like this. It's a 1, and then there are only zeros. And it's a column vector, so transpose. The x1 ket would be the next basis state. and so forth. And we also have then the xn minus 1 ket, which would be all zeros except the last one. So we have these basis states, x0, x1, x2, and so forth. And our psi ket from here can then be represented as a linear combination of these basic states. So our psi ket would be effectively the complex amplitude C0 times x0 ket plus C1 times x1 ket and so forth up to the last complex amplitude, and we call this then xn minus 1 ket. So if we write this out, it would be C0 times the first basic state plus C1 times the next basic state and so forth up to Cn minus 1 times the last basic state. So eventually our psi ket is just a linear combination of the complex amplitudes and the basic states. Is that something, like from the notation, something you're okay with? Maybe just send me a sign if you're okay with that. So what our psi ket is made of. And we also say that this psi ket is a so-called superposition. What this means is it's a superposition of our basic states. The basic states were here. And what we are representing here is that our particle is in all of these positions, which are denoted by the basic states. It's in all of these positions simultaneously. So it's a blending of the xi's, and how much we are in each of the basic states, that's what the complex amplitude or the complex probability tells us. And that's something we will call now from now on always a complex amplitude. But this is an M. It's written properly in the slides. So in the slides, you can find this on page 128 and 129. Now we're doing our quantum experiments, and eventually we also need to do a measurement at the end of the quantum experiment, because when we are running the quantum experiment, we only have these superpositions, and they give us a high degree of parallelism in computation, which is great. But eventually, when the experiment is over, we need to measure and find out in which state we are actually. Measurement is also a probabilistic operation. Well, I mentioned measurement 2 or 3 weeks ago very briefly. We will also discuss measurement today in great detail. But when I measure, I need to, so I'll write down measurement. When I measure, I want to know with what probability am I in position I or xi, and I can calculate this by taking the CI, so one of those, the corresponding amplitude, and I take its modulus, and it's very important, I square the modulus, and I divide this by the length of the vector psi ket squared. This is nothing I have come up with. This is like one of the basic principles in quantum theory. So I take the complex amplitude, I take its modulus, that's what the brackets around mean, and I square the modulus. It's something we had worked with before when I introduced complex numbers and We've done some of these operations together. And then I divide this by the length of the vector squared. And I can also define this more concretely. How I take the absolute value squared of a complex number is something we have learned. And if I want the length of the vector squared, well, what I'm doing is I just take a sum and I go through the individual elements Cj. I take their modulus squared. Usually for the length, I would still put the square root around it, but since I square it, the square root will disappear, so that's gone. And because we calculate these probabilities that way, we will always get a positive real number. So my Pxi will always be less than or equal to 1, and it will be greater than or equal to 0. So this approach here will return me positive real numbers, which are concrete probabilities. There's also some way how this is often visualized, and I will show you this in the slides, because in the slides it's visualized far better than I'm able to visualize it. So this is what I just did. I've shown you the superpositions, and all of this is something I had drawn on the whiteboard. And we've just looked into these equations. And oftentimes you will see in the book, and since I'm taking a lot of the figures from the book, you will see something like this. I have my state psi cat, and then I have this wiggly line, and eventually I have an xi cat here. This line here, this wiggly line, means measurement. So I have a quantum state, and after measurement, I say the quantum system collapses into a classic value, and the classic value would be then the concrete position where my particle is. Because with the superposition, I assume it's in all of the positions at the same time with a certain amplitude, and after measurement, I get a concrete result. But it's very important that measurement is also non-deterministic or probabilistic. So if I run the same quantum experiment twice, I may get different results. It's also something I said in the past. And that's why you need to run the same quantum experiment multiple times. And eventually, you will get a distribution of results. And then if you have a very high complex amplitude for position x0, and you have the other position x1, which has a very low probability or a very low complex amplitude, then most of the time this will return you x0, but sometimes it will return you x1, because measurement is also probabilistic. So a quantum experiment, or the kind of quantum experiments we will use in quantum computing, we have to run the same quantum operation multiple times just to get a distribution of the possible results. And then probably after we run the same experiment, say 100 or 1,000 times, I get a more or less reliable distribution of what the output is. But that's something we also see when we run real quantum computer experiments. Now, from what I have shown to you, we can use an example and calculate these probabilities on our own. I'll switch back to the iPad. I feel writing this down and showing you these calculations live on the iPad is probably helpful compared to doing this only in the slides. So my state psi cat looks something like this. I have a four-dimensional vector. The first one is -3 minus I. The next one is -2i, then I, and then 2. And what I want to know is, I want to know the probability P of x2. So I want to know what's the probability that our particle can be found at the position x2, which is here. So what I need to calculate is, I need to calculate, and we just see it up here, I take the I, which is the probability or the complex amplitude for x2. I take this and I take its absolute value and I square it. And I have to divide this by the length of the vector squared. So we'll do, I'll just write it down. We take the length of the vector squared. What I need to know now, what's the length of the vector squared? And maybe the squaring comes later. For now, I want to know what's the length of my vector psi cat. It's actually straightforward as with regular vectors, but here we just, we don't use real numbers, we use complex values. So the first element is -3 minus I. I take the modulus squared of the first entry. The next entry is -2i. I take the modulus squared plus the next entry, the modulus squared, plus the last one, 2 squared. And I want to know from you what you get here as a result, maybe without looking at the slides, but you can just take these modulus squared. You can add them up and take the square root, and then let me know what you get as a result for the length of our vector psi. And maybe don't look into the slides, but for now, just try to calculate it on your own. Once you have a solution, please send it to the chat. So one student was fast and he says it's the square root of 19, which is correct. Feel free if, and we got a second one who got this as well, so that's great. It's the square root of 19. And now in order to calculate our probability, it's 1 by the square root of 19, but then still squared. So, or simply 1 by 19, 1 divided by 19, which is 0.0526 and so forth. So that's the probability. Good. Since multiple of you send square root of 19, it seems solvable. When we will work a lot with this pra-ket notation now. The ket is something you have already learned. The pra will come later. And essentially these kets, they just represent column vectors, and you can also just add them up. So you can have a psi ket plus a psi prime ket. You add them up, and what you're doing, even though this looks here extremely complex, all you're doing is just you're adding up these complex amplitudes element-wise as you add them up in a vector. So the this ket notation is nothing just but a column vector for now. We will need the pra later, which is something slightly related. We'll see this later. You can also multiply a complex number with a ket as you multiply any scalar with a vector. You just multiply it by every element, and that's what's also shown here, but it's fairly simple. So if you see a ket, all it means is it's just a vector. You can also add a ket to itself. That's more like sort of a special case. We're not discussing this derivation now in detail, but maybe you're wondering what happens if you just add a ket to itself, or you multiply the ket by 2. Does that change this probability? Because just before we had this example here, and I wanted to know what's the probability of finding the particle in position x2. And now if I multiply all of these values by 2, or by just adding ket to itself, eventually it will not change these probabilities at all, because what happens is I'm dividing by the length of the vector, and if the length of the vector just increases proportionally because I have multiplied every element by 2, it doesn't change these probabilities at all. It's derived here in detail, but for now, just trust me that the exact length of the vector proportionally doesn't make a difference. So if you multiply the vector with 2 or with 5 or whatever, eventually these probabilities will not change, because you're dividing by the length squared of the vector, and that leads to a normalization. And here we come to the next important term, normalization. Normalization is something which we will always assume from now. We will always assume to work with normalized kets. So we have a ket, whatever its entries are, we normalize it by just dividing the ket by its length, not the length squared. That's important. The length squared, we only need it for these probabilities, but we normalize our vector by dividing by its length. As you know, that can be done in classic linear algebra, so it can be done with this ket notation. We can also do an example that I will show you now on the iPad. I'm just opening the screen again for you. And we have one example now. So we have a vector, we have psi ket, which is 2 minus 3i and 1 plus 2i. And what I want you is to normalize it. So what we need is first the length of psi ket. And if you have a, or I can quickly start with this. So it's 2 minus 3i modulo squared plus 1 plus 2i modulo squared. If you have a suggestion what this result is, so what the length of the vector is, maybe send it to the chat. That's correct. It's the square root of 18. And now if I want to normalize psi ket, so I have psi ket and divide it by the length of the vector, then I would have my vector psi ket divided by the square root of 19. Approximately, this would lead to something, but just approximately 0.417 minus 0.707i, and the next entry would be something like 0.2357 plus 0.4714i, just approximately. But you're all familiar with how to normalize a vector, something you learned in linear algebra. Now there comes one big advantage when you have normalized vectors. Before, when we calculated these probabilities of being in position xi after measurement, what we said was, well, we have our CI modulo squared, and we divide this by the length of the vector squared. Now, since we have normalized vectors, we don't need a normalization here anymore. So this can be just eliminated. And if you have normalized vectors, just doing that part here is enough in order to calculate the probability of being in that position after measurement. There's a question here if there's any notation for a normalized vector. I've seen different notations in the past, but the book here doesn't really use a notation. So I would also, from now on, we always assume we're just using, or most of the time we'll be just assuming we'll have a normalized vector. But I can quickly check if there's maybe a notation recommended on the internet. So just wait a second. Normalized vector notation. Because I've seen some notation in the past, just checking. Yeah, sometimes people they put like they would write that you have like a psi cat, and they would sort of put a hat on top. Sometimes a hat is a notation used to describe normalized vectors, but we are not using this really in this book, or I'm not aware that we're using that notation here in the course. But thanks for asking. So this is what you call a hat. So a psi hat cat probably would be the way you call this. So I can switch back to the slides. So this is what we just did. We saw how we normalize a state, and I said that after observing the particle, the probability would be like this. We just removed the normalizer because we're dealing with normalized states, and this is the example we just did. Now there comes the question of how you can actually implement such quantum states in a quantum computer. And what is often used is a concept called the spin. The spin is a property of subatomic particles. It's something that I'm not explaining here in detail. If you're curious about the spin and the so-called Stern-Gerlach experiment, there are a few slides here in the slide deck, but I'm skipping them because we don't need this for the level of quantum computing we'll be doing in the next chapter. However, if you're curious about this Stern-Gerlach experiment, feel free to take a look at the slides, or it's also explained in detail in the book, but I'm just personally skipping it because I don't think we need it for the remainder of the course, because it's not a physics course. We're doing a quantum computing course. Now that we have done the cat notation, we will do a quick break until 3 p.m. and then we continue with the next notation. So see you in 5 to 6 minutes at 3 p.m. So welcome back from the break. I know this was quite a lot of notation stuff around this cat notation and a few examples. As we had a cat, there will also be a bra, and the bra looks very similar to a cat. So just remember here as a revision, the cat looks something like this. So psi cat, for example, and the bra would look like this. So I have my psi bra, and a cat would look something like that. And bra and cat are actually highly related. So the psi bra is actually the psi cat, and I apply the dagger to it. And as you remember, my psi cat looks something like this, I had a C0, C1 up to Cn minus 1. And now if I apply the dagger, which is the adjoint operation, this will be a, yeah, correct, it's a row vector. As you remember, the adjoint operation, which we call dagger, what it does is it transposes our structure, so it turns our column vector into a row vector, and we also take the complex conjugate of every element. And the complex conjugate, something we denoted as C0 and put a bar on top, C1 bar, and so forth, up to Cn minus 1 bar. And remember, the complex conjugate is we just change the sign of the imaginary part of the complex number. So the bra and ket are related. So the psi bra is just the psi ket, and I apply a dagger to it. And just to make sure you understand that, we also have an example here. So I have my psi ket, which I say it's a 2-element column vector, 3 and 1 minus 2i. And I want you to write in the chat what the psi bra would be. And once you have this, we can compare your solutions. We got the first right answer. So very importantly, it's a row vector. The first element is a 3, and the next element is a 1 plus 2i. So we've changed the sign from minus 2i to plus 2i. Very simple. Then we will also see, that's probably something I can show you on the slides the best. So just switching to the slides. We will now wonder about so-called transition amplitudes, and we will take advantage of the dot product. Concretely, we will have two normalized states. We will have a psi ket and a psi prime. So this element up here is something we call a prime, so a psi ket prime. And we will say that we have our start state, which is our psi ket, and we want to do a measurement, and we want to know how likely the state of the system before the measurement will change to the end state after the measurement has been carried out. So measurement is something uncertain, and we'll also talk today more about measurements. So what we want to calculate is how likely it is to turn from this state to this state, and we want to calculate that. And so what we can say is we want to extract the transition amplitude between these two states, and our psi ket is the start state, and the psi prime ket is the end state. And we can calculate this transition amplitude the following. I just say I take my psi ket and multiply it with the psi pra. And this is written like this. I have on the right my psi ket, and I multiply it with the psi prime pra. And the psi ket is something you're very familiar with, and the psi prime pra as well, because we just add these primes, and it's a pra, so it's a row vector of these complex probabilities for which we take the complex conjugate. And what we are eventually multiplying is we have a column vector, and we multiply it from the left with a row vector. And that's actually fairly easy. It's actually nothing else than the dot product of these two vectors. And I'm just multiplying C0 prime, and I have the conjugate times C0, which is the first part. Then I do the same for the C1. I multiply C1 with the C1 prime, and which is the conjugate, and so forth. And I calculate this, and this will return me a value that is the transition amplitude between these two states. This can also be visualized again with these weakly lines that we have our psi ket, and we want to transition to the psi prime ket, and the probability for that is, or the transition amplitude for this is what we've just calculated, that it's psi ket from the right, and we multiply from the left the psi prime pra. And that's actually what this bra ket form is very helpful for, to calculate such transition amplitudes. And eventually it's nothing else, but we are taking the inner product. So the inner product or dot product, whatever you name it, slightly two different things. The inner product is slightly more generic. That's what we are calculating with this bra ket form. And that bra ket form is simply very popular in quantum mechanics to describe such effects. We will also do an example for this before we advance with the slides. So I'm just returning to the iPad in a second, and we will do an example together to just make sure you all understand it and you can practice directly. We have the next section. We have our psi ket, and it's a normalized vector. So it's a vector where we have a 1 and an I. So we need to normalize the vector with, we'll just do it like this, 1 divided by the square root of 2. And we have the other one, it's a phi ket. And that's also a normalized state, which is I and -1. And what I want you to calculate is how likely, or what's the transition amplitude to go from the psi ket to the end state, which is the phi ket. And what you need to calculate eventually is you need the psi ket and the phi bra. And if you have a result, what that is, if you calculate it, send it to the chat, please. I want to see if you understood what I just explained in the previous slides. I'll give you a second to try to calculate this. One student says it's a 0. Maybe someone else has a suggestion what the result could be. We have 40 people present, so there should be enough other students trying to do these calculations. Well, we can try it out and see if the result is correct. So what we need is the bra one for this, and that would be then 1 divided by the square root of 2, and we get a row vector. So just putting this away here. And this would be minus I and 1. And now we are essentially just multiplying these two structures. We have from the left the bra. So it's 1 divided by the square root of 2 minus I and 1. And we multiply this with 1 divided by the square root of 2 of 1 and I. So it's 1/2 time, 1 divided by the square root of 2 times 1 divided by the square root of 2. So it's 1/2. And then this is minus I. And well, somehow I made a mistake, I guess, because it should be minus I. So this is now the demo effect. There's probably some mistake. I don't know if someone raised their hand, so probably you spotted the mistake that I made.
Actually, it may be a question, because
okay,
when we had phi cat,
yeah,
we had I and -1, but when you did
thank
the
you.
bracket, we
Yeah.
have 1, but I think
Yeah.
that should be
Thank you.
-1.
Yeah, thank you. I spotted it. Thank you. Because I knew the result is wrong, so I felt I had missed something. Thank you very much. And then it finally works, because then it matches my notes, and then it's again minus I, and so we have 1/2 times minus 2I, so it's minus I, and this is exactly what I wanted. So thanks for spotting where I missed the minus, because I knew the result didn't make sense. So, but that was a good practice for all of us, and we could calculate these amplitudes for the transition. I know all of this still looks very abstract, but we are now looking at this from the quantum mechanical perspective, and in the next chapter we will do all of this for quantum computing, and we'll deal with qubits, which will make it slightly simpler, because we're just dealing in fact with very small vectors. But now we're just looking at it from a more generic perspective, because once we understand it from the generic perspective, it will actually be super easy to use all of these constructs for quantum computing. If you take a look at the slides, or we can quickly look at them, as you have noticed in my slides, there are obviously always there's a lot of text, and the text is not for me to be read out now. The text is for you when you do revisions, and if you need any further readings, that's why there's a lot of text in these slides. Sometimes this amplitude can be 0, for example, for two states that are mutually exclusive, if you're just unable to go from one state into the other. That can happen sometimes, and then that could also be 0. And what you have also noticed before, when we started introducing our quantum states, we said a quantum state is a linear combination of basis vectors and the complex amplitudes. In fact, what is required that our basis states are an orthonormal basis. Anyone knows what an orthonormal basis is? If you ever heard this term, maybe send a green sticker. If you never heard about that term, maybe send a red sticker. I don't know if that's a term that you all saw in the linear algebra introduction. So some have not seen that. So an orthonormal basis means you have a vector space in which all your basis vectors are mutually exclusive, because they are all orthogonal to each other. And that means you then have an orthonormal basis. So that's the term. Orthonormal means you have all the basis vectors are orthogonal to each other. So in case you heard that, you never heard that. And an orthonormal basis is important for these quantum experiments. You can obviously use a different basis. You don't need to use the basis we are using here. You can use different bases. And when you take an introduction in linear algebra, you learn how to convert vectors from one basis to the other. That's probably something you have learned as well with some linear transformations. If you take a look into the book, this is elaborated in much more detail why we need an orthonormal basis. But here we just say we need the orthonormal basis. And once we do quantum computing, we're anyway just dealing with 2 entries in every vector, and it will be fairly simple. So we don't need to discuss this here in detail for linear, for quantum mechanics. Feel free to read the slides. You're obviously most welcome to read them, but it's just something that I'm skipping through because we will not need it for quantum computing, which is the goal. But one thing that is important now, I said we have our state. So for example, psi cat, and we measure it, and we can eventually, through a measurement, get one result. We measure again, we get a different classic result, let's say in a qubit, which would be the most simple one, which is the 2 basis states 0 and 1. And you either get a 0 or 1 after you do the measurement of the quantum experiment. And that's why you need to run this experiment multiple times, because there is uncertainty in the measurement. And this is what's visualized here. Say you do the measurement, and when you do a measurement, your quantum system collapses. So this is the term we use, that it collapses, and it means it collapses from a quantum state to a classic state. There are different outcomes of the measurement, and how to calculate these probabilities that it collapses into each of these basis states. This can also be described with the Bra-Ket notation, because we have our, I'm zooming in a bit to show it, because we have our state psi cat, and B0 would be the first basis state, B1 would be the next basis state, and I calculate the psi cat and multiply from the left my B0 bra, and this would give me the probability that the quantum system collapses in the first classic basic state, with B1 in the next one, and so forth. So this is essentially the idea of doing a measurement, and you can calculate each of these probabilities that it ends up in one of these classic states like this. For qubits, it will be easy, because when we work with qubits, we are in parallel in 0 and 1, and when we measure, we're either in 0 or 1. But obviously, this chapter is more generic, because it's not just about 0 and 1. It's about larger or more complex quantum states. And we're discussing this from a more generic perspective, and then it will be super easy when we do quantum computing in the next chapter. This is what we had just done when we calculated the transition amplitude from one state into the other when we measure. And these vectors here are normalized. I wrote them in a slightly different way on the whiteboard. I didn't write square root of 2 divided by 2. I wrote 1 divided by the square root of 2, but that's just the same, because a 2 is square root 2 times square root 2. So you can cancel it out in the numerator and denominator. But the book often uses this notation, like a square root of 2 divided by 2, rather than 1 divided by the square root of 2. That's somehow the preferred notation in the book. But I think it makes it unnecessarily complex, and that's why I wrote it in a simpler way on the whiteboard. But these states are normalized, and that's why we could just very easily calculate the phi bra with psi cat. that's what we calculated, and we got -1. But what we wrote is we had a phi pra and a psi ket. And what we calculated is exactly the same as if you just take the inner product. So this pra ket or ket from the right and from the left, a pra, is just the same as calculating the inner product. And the inner product is something you learned when you studied linear algebra, or you called it a dot product, whatever. While the inner product is something like slightly more generic. If these vectors are not normalized, you can still calculate this, but you need to use a slightly different formula, because you cannot just use your pra ket, but you would need to divide by the product of the length of the two vectors, because we have our phi and our psi, and you would sort of need to calculate their lengths and multiply and divide by the product. Then you would get a proper result. But since we only worked with normalized vectors, we don't need to divide by this anymore. So this is only a note in case you're using unnormalized vectors. There's also a long example, just the same example we did before in on the whiteboard, but here we're doing it with these unnormalized vectors, and we're just calculating the dot product again of the unnormalized vectors, and we have to multiply by the product of these two lengths, and eventually it gives us the same result. Feel free to double check it at home. It gives you the same result, but we worked with normalized vectors in the beginning anyway, so we didn't need to worry about that in the first place. So now we are okay with states and measurements. And if you now look into the book goes very detailed into something that is called an observable. So an observable is a quantity you want to be able to observe when you measure at the end. In the book, this is explained throughout like half a chapter or something, what observables are and how they work and how you can measure observables, especially say if you had multiple observables. It's something I have made a few slides on, but I'm totally skipping through this, because if you're curious about how observables work, this is in the book, but you don't need it for this course, because this course is not a quantum physics course. This course is a quantum computing course. So it will become fairly easy for us what the observables are. The observable for the qubit is if the qubit is when we measure, if it's either in 0 or 1, so which of the two classic states we get. So I feel we can skip most of this theory about observables. But if you're curious how these observables work and what kind of operators they are, this is explained in the book, but you'll need this largely if you're interested in quantum mechanics. For quantum computing, all of this will become super trivial in the next chapter, and that's why I'm skipping through these observables. The term measurement is something I've mentioned now a few times. Remember, when I have a quantum state and I measure, I not always get the same result. There's also uncertainty coming in through the measurement. And that's why I need to repeat the experiment multiple times. And that's one of the contributors to uncertainty in all of this. And when we run real quantum experiments in a few weeks, you will also notice this. When you run, we will, in a few weeks, there'll be a lab session, and we have a Jupyter notebook that you can try out. You can either simulate this or on your computer, and you can also create an account with IBM, and you can run this on a real quantum computer, and you can run the experiment many times simply to see how the possible results are distributing, and you see the measurement will add some uncertainty. When you simulate it on your computer, you can obviously sort of manipulate this a little bit more, or you could sort of make the measurement fully certain. If you wanted, you could do sort of a majority pick, but in the real world, there will be uncertainty introduced by the measurement. And the measurement is only one thing that adds uncertainty. The other thing that contributes to uncertainty in quantum computing is decoherence. it's something that I think Horst Kuhnhardt mentioned last week a little time, or for a short time. That means if you keep running the experiment over a longer period, your computer, your quantum computer, will interact with the real world, and you will also lose information. But that's the other contributor to uncertainty that we will discuss in a few chapters. So there are two contributors to uncertainty in quantum computing: decoherence as well as the measurement. And there are a few more details on measurements, again, in a highly generic space, but we only need all of this for quantum computing. If you're curious, do further readings. I think the book explains this very well. Now, we have introduced states. We also talked about how to measure states, but actually in a quantum computer, we need to do more than create a quantum state and then measure. We actually want to do computations. So we want to evolve states into next states, step by step, do our operations, and then measure. And for that, we need to think a little bit about dynamics. And that's something I will visualize again on my iPad, because then it's probably more obvious if I develop the figure step by step. So imagine I have my state psi, and I always called it psi ket. And now this is obviously not static, but I will slightly amend this notation now and say psi at time t ket. So this is a parameter because the system will evolve over time. We do multiple operations. And my system is now at time slice t, and I apply some operation to my state now to transform it into a new state. No measurement yet, but some operation will be some fundamental operation in quantum computing. We will see them in the next chapter. Like in a classic computer, you have an AND gate, and so there are other gates in quantum computers. But all these gates and all these operations in general will be described by unitary matrices. So unitary matrices, you remember, we've seen them now a few times. Remember, their property is if I have a U, which is my unitary matrix, and U dagger times U is the same as U times U dagger, and this must be the identity matrix, which is a very important property because it allows us to undo operations. And U is a matrix, so that's an operation which I apply to my vector. So the vector is the psi at time t ket. And this will then lead to a new state. And the new state I would call sort of psi at time t plus 1 ket is this. It's the old state, and I transform it into a new state by multiplying from the left the operator. And this is how I will have this evolved. And I can now try to visualize this in a slightly more complex way. And we also see that we are able to undo operations. So I will have my state psi, and I will then, and I'm sort of copying the figure I found in the book, I will have and the psi here. I'm just building it step by step. You will soon see what this is useful for. I want to go from psi ket into some future state, and for this I use a unitary matrix, and you'll find this figure also in the slides. And I say I use a matrix U, say some matrix U at a certain time point t0. So this is some operation U at time 0. And the state that I'm getting will then be not written out, but it's our psi ket times this matrix U at time t0. So this here describes a state. I can also undo this operation, and I can go back from this state to the previous state by multiplying my state with a unitary matrix, which is U at time t0 dagger. And then if I multiply this dagger here from the left, then the U and the U dagger will undo each other because they are both the same from the same time slice t0. I can also, rather than undoing it, wrong color, this, I can use another operation, for which I use a different color now. It's U at t1. So this was the state, and I still copy this over here. Oops. So this state here now is my psi ket multiplied with this matrix at t0, then at t1, which is a new state. And if I want to undo this and go back to the previous state, then I need to use U at time 1 dagger. And then these two will sort of undo each other. And then I can go back, for which I only keep this part. So this is the idea of this dynamics. It has to be symmetric in time. That means if I have this state here over here and I want to undo an operation, I can only undo the most recent operation because I multiply these operations always from the left. So I cannot suddenly sort of use this one here and then undo something from over here. That doesn't work. I first need to undo the most recent operation. So this is symmetric with respect to time. And this is a very important concept in quantum computing, because when we start looking into quantum computing in detail next week, we will see that we can create, that we have start states, we do operations, but sometimes these operations lead to unnecessary superpositions. And this would make subsequent operations maybe more difficult. And at some point, we have to undo some of these operations to evolve. And that's why undoing operations is super important in quantum computing. And to be able to undo operations, we describe all of our operations in terms of unitary matrices. And this is visualized in here now. It's also visualized in the slides, which I'll show you. So this is just what I copied here for you, and I just copied the first few steps. Yeah, I just copied this part here, and they use this other font for you, but that's just what I had shown to you, and it shows I apply to the right new operations, and I can always undo the most recent operation and go back. And to be able to undo operations, that's something that you can often not do in classic programming. Say if you have an AND gate, you have two bits that go in and you take an AND, then you lose information. You cannot just undo an AND operation. There are obviously some operations you can undo, like a negation, but say an addition is hard to undo, an AND or an OR, because each time you lose information. And in a quantum computer, we will only use operations that can be undone. There will be new operations using quantum effects. And then we use something or an approach that is called reversible computing, because in reversible computing, we can revert operations. So now, as usual, there's more in the book to read, but I guess on dynamics, I've just shown you the most important part, and we don't you don't have to read chapter 4.4 anyway. All these further readings, it's great to read all of this, but I know you have limited time. That's why I show the essence. There are a few more readings in the slides, a little bit of text. And if you're super curious, take a look at the book, which is anyway available in the Nextcloud directory. Now we can go ahead with assembling quantum systems. When we started today, we looked at how we can assemble systems, and we used simple probabilistic systems for this. Just to get started, we can obviously assemble quantum systems, and it's something super important we will need for quantum computing. But when we build these multi-particle quantum systems, some strange new effects, in particular one that we call entanglement, will start to appear. So what we have is we have a quantum system Q and a second quantum system Q prime. And they are represented by vector spaces V and V prime. And if we merge these two quantum systems Q and Q prime, we represent this by the tensor product of V and V prime. Because before, when we started assembling quantum systems, we saw we can describe all of these transitions just by taking the tensor product. And this is just a quick summary or overview about what we have done. We can do this for more than two systems. We have done this so far with two systems, but you can do it with three systems, with four systems, with five systems, with K many systems, and you build just much larger systems. If you do that, obviously this transition matrix will get quite big, but it can be done. Feel free to try it out. Also, maybe try out an example on your own with two quantum systems. You have seen it today. Take three systems and try to assemble them and see how the matrix gets bigger. And for quantum computing, that's important because maybe you want to combine 10 qubits into something, so you need to combine 10 systems because each qubit is a system. Then I'm just checking if this one can be skipped. Yeah, we've seen what the tensor product looks like before, and it's important to always put these comments to the left. And what is also important is, say we're now combining two quantum systems, and each system has two positions, so n and m, both is 2. And before we talked about these basic states, and we used the basic states when we started with the definition of a quantum state, and we said essentially it's a linear combination. Now, when we build our quantum system, we also need to be thinking about the basic states in our assembled quantum system. X0 is the first basic state of the first quantum system, which could be, for example, just a vector 1, 0. And X2 is the next basic state, which is just 0, 1. But then you also have your Y0, which could be just 1, 0. And Y1 could be 0, 1. So these could be the simplest possible basic states. There can be different basic states. The only requirement is that in a system that these basic states are from an orthonormal basis. We've looked at the simplest orthonormal basis, like 1, 0, 0, 1, and so forth. There can be different ones. And you've probably seen such stuff also in a linear algebra class when you looked at different bases and how to convert from one basis to the other. But now we also need a basis when we build our composite systems, or we assemble these systems. And what is typically then done is we have our x0 and we take the tensor product with y0. So we take these basic states and we take the tensor product. This would lead to the first basic state in our assembled system, then the x0 and y1. We take the tensor product. What we get from here would be the next basic state of the assembled system, and so forth. And then I think I'll write that. Otherwise, it's just probably too boring for you if I just show this from the slide. So I'll just write that. Also make sure you fully get it. So in the assembled system, I have my psi ket, which refers to a vector in now an assembled system. Then I have these basic vectors, so x0 and the tensor product with y0. And still correction. So x0 ket and y0 ket, the tensor product. And I need to do this now for these three other ones. So just writing down these four basic states. Before we saw that this would be x0 and y1, x1, y0 and x1 and y1. And it's a linear, so our state in the assembled system is a linear combination of these four basic vectors. And here I would have my first complex amplitude, so C0, 0, C0, 1, C1, 0, and C1, 1. So these are the complex amplitudes. And remember, we have a normalized system. That means there's a certain constraint as before on a quantum state on these complex amplitudes, so that their modulus squared add up to 1. Then all of this also applies now to an assembled quantum system. The same requirements we had for a quantum system apply here as well. So this would be with this 2 times 2 system. Obviously, it can be more generalized for m many and n many. And we could try to write this down as well. So I have my psi ket. And now we generalize this a little bit more with x0 and y0. And we say ... to generalize. We have the xi ket and the yj ket. And again, ... because m and n are larger than 2 now. Plus, we say the xn minus 1 ket and the tensor product of y m minus 1 ket. And then again, we put these complex probabilities here. So this would be C0, 0. This would be Cij, and this would be Cn minus 1, m minus 1. So this would be a vector in an n times m dimensional space, and it's a complex space. So the vector would be in that space of complex numbers where it's an n times m dimensional space. So this maybe looks very tricky or cryptic now because I'm adding all these indexes, but all I'm doing is here I'm assembling a quantum system. And I have the same requirements that eventually the complex amplitudes are normalized, so that our amplitudes modulo squared sum up to 1. Something we have seen before, and it applies here as well. So then we can have an example, and I'll show you the example here as well on the whiteboard. You can also find it in the slides, but I think if we develop it step by step, it's more fun. So the psi cat is now a linear combination of, again, it's a 2 times 2 system. So x0 cat tensor product with y0 cat. Just writing this again, but with concrete numbers. So x0, y1, x1, y1, y0, x1, and y1. And now I'm putting in concrete complex amplitudes. The first one is an I, and then the next one is a 1 minus I. It's a 2, and a minus 1 minus I. You remembered before how we could calculate, and I can just move back to see this. We wondered about how can we find out that a particle is in a certain position after measurement. We saw this, including the normalization, but when we said it's normalized, then we just looked this one here. But when it was not normalized, we used this equation here, and this is how we could determine what's the probability of finding the particle at that position when we measure. Now we can apply exactly the same concept to assembled systems. And I'm curious now, what's the probability of finding the particle at x1 and y1? What we need to calculate is, so x1, y1 would address this one here. So we would need to calculate the modulus squared of this one here, minus 1 minus I squared. It's not normal, so these complex amplitudes are not normalized, so we need to divide by the length squared of this vector, and the vector is just what I'm highlighting here in green. So what I need to put in is an I squared, a 1 minus I. We take the modulus squared, we take the 2 squared, and the minus 1 minus I modulus squared. And I'll give you a moment to try to calculate what the result of that is. And when you have the result, post it in the chat. And then we know the probability of finding the particle in the composite system in x1, y1 after measurement. Eventually, all of this looks tricky and cryptic, but it isn't too different to what we have done before. Now we just use composite systems, and each entry in our vector refers to a composite element, but the math is pretty much the same. So if you have a suggestion what the number is that I'm looking for, so what I have just shown you, let me know. And try to calculate these modulus squared and then send it to the chat. It's correct. It's 0.222, so it's 2/9. That's correct. So we got at least two answers that are correct. Good. We'll do again a 5-minute break until 3:55. And then we look at entanglement, which is an effect that can appear in composite quantum systems. And then we'll also be done with most of today. So see you in 5 minutes. So welcome back from the break. And we'll now look at an effect that is called entanglement. And entanglement is a very property of composite quantum systems that will give us opportunities in quantum algorithms that we see later in this course. But first of all, entanglement is a generic concept from quantum physics, and in quantum computing, we'll try to exploit it. And entanglement is something that is really strange, first of all. So we've seen these basic states of our assembled system, and they are just tensor, they're just a tensor product of basic states of these systems of which the composite system is built. And now you're wondering if every state vector in a composite system can be written as the tensor product of two states, one coming from the first quantum subsystem and the other one from the second quantum subsystem. You would probably think, yes, every state in our composite system can somehow be broken down into this tensor product of the two states coming from the subsystems. But it turns out it is actually not that easy. And there are states in a composite system that cannot be broken down into two individual states from the subsystems. Showing what's the idea behind this is, again, probably the easiest on the iPad, because it takes a little bit for us to build this, and I don't like oops, I'll try again. Somehow this didn't work. Just wait a second, please. Oh, now should be working. So we will start now in entanglement with a state that we call psi ket. And it actually looks a little bit smaller than these generic states we had seen before. It's x0 ket tensor product with y0 ket plus, and I'm writing it down here, x1 ket tensor product with y1 ket. And you think, well, that's now a quantum state in the composite system. We can actually try to write this a little bit more concretely. So what's maybe missing is the complex amplitude. It's just a 1. I'm highlighting this. And there's actually, that's it. But maybe let's write down what we don't see, what is actually maybe missing. And it's these parts for x0 tensor product with y1, and for x1 and the tensor product with y0. And those are actually 0 because they didn't appear initially. So I'm just putting this now in a box that this was not there. And since it's 0, it's not there. But I'm just highlighting it if, or it's just that we see what we actually did not write down. And now for our psi, which are just these components with a 1, we can sort of see, or we can sort of try to break this down into states from the first system. Every vector representing the first particle So I'm writing down first particle, every vector from the first particle, so from the X system, which are x0 and x1, these are the two positions. Every vector representing the first system can be written as C0 times x0 plus C1 times x1, and x0 ket and x1 ket. That would be a vector from the first system, and from the second system, or the second particle, so the particle that is in the second system, we can also try to write that down. And we can write, well, it's a C0 prime times y0 ket plus C1 prime times y1 ket. And this is from the second subsystem, because our psi here is from the assembled system. And now we can wonder if our psi can actually, so the psi we have here with these two components, if this can actually be written as the tensor product of the two subsystems. And we can try to write that. So we can say that we have our, we now build, or I write in a generic way, such a state, because what we see is our psi ket has only elements from x0, y0, x1, and y1. So x1 and y1 together, and x0 and y0 together. We don't really combine x0 with y1 or x1 with y0. And now we want to describe such a state, and we can say, and I'll write it down and then I'll explain it. So we have a state from the first system. We had this here, and from the second system there. We can say, well, I have my complex amplitude C0 x0 ket plus C1 times x1 ket. And we take the tensor product with a state from the second system, so C0 prime times y0 ket plus C1 prime times y1 ket. And we can try to write this out now. You're all familiar with the tensor product. So we can try to write this out. And so there will be an x0 ket in the tensor product with a y0 ket. There will be a x0 ket in the tensor product with y1 ket. We will have the x1 ket in the tensor product with the y0 ket, and the x1 ket in the tensor product with y1 ket. And now, since we are taking this tensor product here, we are just multiplying the corresponding complex amplitudes. So for x0 and y0, this would be c0 and c0 prime. So the c0 coming from here and the c0 prime from there. Accordingly, for the next element, it's c0 because there's an x0, and the c1 prime for the y1. Then the c1 and c0 prime, and c1 and c1 prime. But here comes the tricky part. For our psi ket, where we only have the x0, y0 tensor product and the x1 and the y1 tensor product, this would mean that, I'll highlight it, that this here needs to be 1, and this here needs to be 1, So this must be 1 and 1. And these two products must be 0, because we just want to have the x0 tensor product with y0 and the x1 and the y1, but we don't want to have these other parts. So that one is something we would have to be able to solve. So I'll write it down. We would have to write C0 and C0 prime must be the same as C1 and C1 prime. This must be 1 plus the second condition is the C0 and C1 prime must be the same as C1 and C0 prime must be 0, because those are those two parts, and these are the two other parts. And here comes the trick. These equations have no solution. You're unable to solve this. So what we can conclude from that, so I'm just putting here something like this, lightning, we're unable to solve this. So we can somehow conclude, even though I'm able to write down my psi cat, I'm unable to build it as a tensor product. And that, I know, looks strange, but this brings us now to the property of entanglement. And the psi cat is actually a state that is entangled. Entanglement in physics means, say, our psi cat is entangled of x0 and y, or x and y are entangled. And the consequence of entanglement would be, if I find out that my particle is at x0 or at x1, I will directly know if it's at y1 or y0, because what I combine is which was this one here, x0 and y0, and x1 and y1. And when eventually, when I measure, it's either in here or there. But this is x0 and this is y0, and I have x1 and y1. And that means when I measure one of the subsystems, I have automatically measured the other subsystem as well. So if I know the position, if x is in x0 or x1, I will automatically know if the other particle is in y0 or y1. And that's the idea of entanglement. And the state that I had shown you here is an entangled state, because we don't combine x0 with y1 or x1 with y0. And that means entanglement. And entanglement is something really strange that also sort of kept researchers like Einstein busy. Einstein once said, entanglement is a spooky action at a distance. I don't know if you ever heard that statement. So when you measure a subsystem of an entangled state, the other subsystem is automatically measured too. And entanglement travels faster than light. So even if these two subsystems that are entangled are super far away, the entanglement, so that you measure one subsystem and the other subsystem is automatically measured too, that one goes faster than the speed of light. How much faster? That was always a big question. And around 10 years ago, there was a physics experiment that showed that the quantum information of entanglement, that travels faster than at least 10,000 times the speed of light. I know that sounds strange, and it's also something that kept people like Einstein busy. They understood it's faster than light, but they didn't know how far that was, or how fast that was measured 10 years ago. Now you're wondering if you can use entanglement for high-speed communication, so to communicate faster than the speed of light, like in Star Trek. Well, it doesn't work that way. So that kind of mechanism cannot be used for communication. Now you're wondering, what is entanglement for? First of all, it's a basic property of quantum mechanics. However, there are also some good applications for it in a quantum computer that will help us to speed up computations, for example. But that's something we see in one of the following lectures. So states that cannot be broken into these basic states are unbreakable. We call them entangled states. And states that can be separated are called separable states. And just a very simple state like we've seen before, like this psi prime ket, that one is not entangled and it's separable into the basic components. You can find more information on entanglement in the book if you want, but there are consequences of entanglement on quantum computing. For example, there are applications in cryptography. You can speed up computations because if you have qubits entangled and you measure one qubit, the other ones are automatically measured as well. So this can lead to improvements in the speed of computational time, plus many other applications. So here comes the good news. We are now done with the quantum theory. I know this was a lot of theory today and in the last 2 weeks as well. So just a quick recap, what we did in those 4 chapters. We started with a motivation, then we looked into the mathematics foundations, complex numbers, linear algebra, complex linear algebra, and we saw that. And then we looked into systems as a motivation, how we can transform states into other states. We started with deterministic systems, then probabilistic ones, then quantum ones. Then we assembled systems. And today we looked in detail in quantum theory. From now on, the quantum states will become much simpler because we will deal now with qubits. We still have a little bit of time, so I start talking a little bit about quantum computing, and next week we will go ahead with architecture. Today we will still look at bits and qubits. We'll see the difference, and then we actually want to build quantum gates, and we will describe our quantum gates in terms of matrices. But just in order to build that mechanism, which is very much linked to how we build systems, it's quite a big step to go from bits and qubits to quantum gates. So we will first revise our classic binary gates that we know from classic Boolean logic and not or. We will try to describe them in a matrix representation. And once we have done this, we can actually very easily build quantum gates. We will look a little bit at reversible gates because the quantum gates need to be reversible because they are represented by unitary matrices. And then we have all the building blocks to build quantum algorithms. There are a few things we will still look at the end, like the mixed states and the no cloning theorem. But once we're at the quantum gates, we have all the building blocks to build quantum algorithms. That means one of the following chapters will be quantum algorithms. And Horst Kunhardt, he will again come into play when it's about quantum computer architectures. For programming, there's also an assignment, so this will still take a little bit. But once we have all the building blocks, we can actually look into selected algorithms. Now, a bit is the very basis of a classic computer. And a bit is either 0 or 1. And this can mean also different things, like it's considered to be true or false, a switch is on or off, or electricity travels through the circuit or not, or high voltage or low voltage, whatever. So there are different ways what a 0 and 1 could mean. And now when we look at our classic bits, we can try to represent them also in our ket notation. We've seen the ket notation today for quantum states. And we can now try to represent our classic bits also in this cat notation. So a 0 cat would mean a 1 0. So the 1 here means it's off or false. This is the 0. So this 0 and 1 at the left, they're just commons, the ones in bold, but the 1 would mean value 0. And if I put a 1 here, that means the value 1. So a 0 cat just represents the value 0 in a classic bit, and a 1 cat represents a 1. And in a classic bit, I say it's either 0 cat or 1 cat. They cannot be combined. That's a classic bit. And now in the quantum world, we are able to combine these two basic states in a qubit. So we are partially in 0 and partially in 1. And that's the idea of a qubit. It's a quantum bit. And just that it doesn't get too boring looking at slides, I will do the last few slides interactively and develop them here on the whiteboard. So a qubit, or just qubit, or quantum bit. And the qubit can be written in the following way: C0 and C1, where the first complex amplitude stands for the value 0 and the next one stands for the value 1. And we still have all the constraints we have on a quantum system that we have learned before. So we looked before at generic quantum systems, and now we have all these constraints here as well. So the modulus of C0 squared plus the modulus of C1 squared must be 1. This is something we learned from quantum systems, so it also applies to our qubits. And our C0 modulus squared, what does that one mean? This is to be interpreted as the probability that after measuring the qubit, it will be found in our basis state, and the basis state would be the 0 cat. Whereas the C1 modulus squared would mean that's the probability after measuring this qubit that it's found in the 1 cat. And 0 cat and 1 cat, they are classic states, classic 0 x or 1. And when I have a qubit and I have these complex amplitudes and I measure it, I get a 0 or 1, and I measure it again, I get a 0 or 1, and I run the experiment a few times, and then hopefully I get a reliable distribution. Because as you know, measurement adds uncertainty. That's what we've discussed today. So in that sense, we could say a classic bit is just a special type of qubit, because these, we could say it's either C0 or C1 are 1, and the other one is 0. So you could say, well, a classical bit is sort of just a special case of a qubit. Yes. And what I have here to write a qubit, this can be written in a few different notations, and I want to show you them because then it will be more easy when you look at other references. So I say my C0 and C1, I can write this again as a linear combination. So C0 times the basic state plus C1 times the other basic state. And we've also looked at these basic states just before. So this one here would be a 0 cat and a C1 times the 1 cat. So this is 0 cat and 1 cat, which are the basic states. And there are all sorts of other ways how sometimes you could see this written. Say we have a different qubit, an example qubit, which would be 1, 1, 1, 1 would not be a valid qubit because we require that the qubit is normalized. And this one here is not normalized because the length is not 1. So I need to normalize this. And the factor for this qubit is then 1 divided by the square root of 2. And this here can be written in so many other ways. And all these ways that I'm writing now are equivalent. I just want to show you them, that you see that it's actually not that difficult. So I have this constant factor before, and I can also factor it in. I can multiply it with every element because it's just a vector, and I multiply every element with this factor. So I can say 1 times 1 divided by the square root of 2. So this is the first element, and the next one is also 1 divided by the square root of 2. And this is a normalized qubit, so it's a proper qubit. And I can use this notation from before with using these basic states, and I can just write, well, it's 1 divided by the square root of 2 times 0 ket plus 1 divided by the square root of 2 times 1 ket. So this is another way how I can write it. I can also write this, for example, because I have the same factor here, I can also just write this as 1 divided by the square root of 2 and say, well, this is a 0 ket plus a 1 ket. And then you can write this again slightly differently. You move this into the denominator. So you can say 0 ket plus 1 ket divided by the square root of 2. So all of this means exactly the same. It's just a different way of writing this qubit representation. So this is a very common example for a qubit. This is something we actually call an equal superposition because the two amplitudes are exactly the same. So that's why equal. So an equal superposition. Another equal superposition would be just compared to what we have done before. We could say another qubit is something like this, 1 and minus 1. So the amplitude is once 1, the other one is minus 1. Also a valid qubit once I normalize it. And we can again write this in so many different ways. We can factor it in. So 1 divided by the square root of 2. And the other one is minus 1 divided by the square root of 2. Then I can write again 1 divided by the square root of 2 times 0 ket. And then I write minus 1 divided by the square root of 2 times 1 ket. So the minus comes from here. And I can write 1 divided by the square root of 2, so 0 ket plus 1 ket. Excuse me, obviously not a plus. That was a mistake. Minus 1 ket. And I can again write this in this fraction way, so 0 ket minus 1 ket divided by the square root of 2. Normalization is very important, as you know. So if I had a qubit that I, for example, just call V, and one of its complex amplitudes is 5 plus 3i, and the other one is 6i, could be also one way how you write it. This qubit is obviously not normalized, so you need to normalize it. So we need to know its length. So the length of the vector is, you can either calculate it at home or you just trust me, it's the square root of 70. How to calculate the length of this vector is something we've done so often. And we can now normalize the vector, so just by dividing it by the square root of 70, which would then be 5 plus 3i this divided by the square root of 70, and 6i divided by the square root of 70. And using these notations from before, we could say, well, this is 5 plus 3i divided by the square root of 70 times 0 ket plus 6i divided by the square root of 70 times 1 ket. And you can then probably wonder what would be the probability of V0. The probability of V0 would mean when I measure the qubit, what's the probability of finding it in 0 ket? So in the basic state 0. If you calculate this at home, you will see that this is 34 divided by 70. So that's the probability of it being found in state 0 ket after measurement. So overall, it's not very tricky. You just now don't have a 1 up there. You have a complex number, 5 plus 3i, and it's done. So all I have told you now is also in the slides. I'll quickly go this through with you, and then we'll also be done soon for today. So we've seen a qubit is defined like this with this constraint. We've seen this. We didn't see this one here, but a qubit, when you measure it, it means you either measure it in the 0 ket or the 1 ket, and we have these probabilities for the measurement, but I've just talked about these probabilities and these different ways of how to write a qubit. We've seen this here, we've seen this here now, and this is just what I had developed on the iPad, how to write all of this. And then one example of how to normalize this qubit I had also just shown you, but I didn't do this calculation here in detail. I only said it's the square root of 70, which is the length. So now we say, well, we have these qubits, that looks great. How can you do this in practice? When you build a real quantum computer, somehow you need to be able to build it in a way that it can exhibit these quantum effects. So you somehow need to build qubits, and there are different architectures that have been proposed over the year. Like you could use a photon, which might be in one of the two polarized states. You can use electrons. You can use other subatomic particles and use their spin direction. These are some suggestions that were made in the literature, but all of this will be explained by Horst Kuhnhardt in his lecture in a few weeks on how to concretely build a quantum computer. The goal of this chapter is that we look at architecture, architecture meaning what are the fundamental building blocks, which are the fundamental computations, not just like an AND gate in a classical computer, but here we need different gates, and we will develop them next week. What we have seen today is we looked into quantum physics, and we understood the foundations of quantum theory, and now we started looking into qubits. And next week, we'll continue, and you see all these notations like the tensor product, and so we'll definitely need this. And we will actually start to look into the classic gates we know from Boolean logic, like the NOT gate, the AND gate, and the OR gate, and we will try to describe them in terms of matrices, which is just a practice to understand them better. And we look then how we can combine them and which matrix operations we need. And once we have done this, we will look at reversible gates, and then we look at quantum gates, and we see how we can combine them together into bigger operations. But all the math foundations are there now because you know complex linear algebra. You've seen all the relevant quantum theory, and we just then look at the fundamental computing units. Like a Toffoli gate is a very common gate in quantum computing, and we look at all of them and how we can build larger operations. We will see the unitary matrices again, and we will finish that next week, and then we can start looking into quantum algorithms. So now we're really in the quantum computing part. At the end of the third lecture of mine, and in total the end of the fourth lecture, I know it took a little bit to get here, but we first had to build all the foundations, and from there we can now actually start doing computing. Do you have any questions so far? If you're okay with today, I know it was a lot of stuff today. If you're okay, green sticker. If there are any open questions, maybe red sticker, and I'll wait for you to turn on your microphone or to send a question here in the chat. The math and the physics theory is now set up, and as of here, we can start doing more and more quantum computing. And there's a question here, which paragraphs would be great to read in the book? Check the slides. Sometimes I write in the slides like further reading, and that one would be cool to read. You don't need to read the whole book. If you read the whole book, that's obviously great, but maybe just take a look at the sections for further reading that I put in the slides. All right, so we're done for today then, and I'll see you next week at the same time for the lecture, which will be fully on quantum computing then, since we have built the foundations. Have a good weekend. Take care. Bye-bye.